The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everybody. My name is Thomas Mueller. I'm a product manager at Bruker. I'd like to welcome you to this installment of our Bruker AFM webinar series. The presentation today is titled High-Resolution Quantitative Kelvin Probe Force Microscopy Principles and Applications. It is presented by Dr. Chunzeng Li of Bruker AFM. Before I introduce Chunzeng, I'd like to make a few quick logistical comments. First, we encourage your participation during the webinar. If you have a question, please type it into the questions dialog box on your screen. We'll accumulate these questions through the presentation, group them together, and then answer them at the end of the prepared remarks. Quite often, we have more questions than we can answer in the session, and in those cases, we'll be sure to follow up with answers via email afterwards. Also, if you'd like to review the presentation afterwards or pass it on to a colleague, the webinar will be posted online within 1 week in the webinar section of the Bruker webpage. As a follow-up to this presentation, you'll also be receiving an email with this link. Finally, when you exit the webinar software, you'll be asked to take a brief survey. We'd very much appreciate it if you take the time to complete this, as it helps us pick the topics that are most important to you and to generally make the series better. So let's get started. Let me introduce our presenter, Dr. Chunzeng Li. Chunzeng is our application scientist for electrochemistry and electrical AFM applications. He's been with the company for 12 years. Chunzeng received his PhD in electrochemistry from Xiamen University, China, and he's the author of 26 international publications and 1 patent. So let me turn it over now to Dr. Chunzeng Li for the actual presentation.
Thanks, Thomas, for the introduction. And thanks, everyone. Good morning. So again, this is Chunzeng Li, application scientist at Bruker Nano Surface Division. Today I will talk about high-resolution quantitative Kelvin probe force microscopy. I will talk about the principles and applications. So mainly I'll focus on one new mode that's called PeakForce KPFM. The outline on my talk. So I'll give a little bit background on KPFM, Kelvin probe force microscopy, and then I will introduce the new mode, PeakForce KPFM. So for this mode, I want to talk about the improved spatial resolution and its accuracy, and the improved repeatability. The reason behind it is we want to make this mode quantitative. Another benefit of this new mode will be it's combined with the PeakForce technical mode, quantitative nanomechanical property mapping capability we have. And in the end, I will summarize. So now let's take a look how many ways we can do KPFM. We know that KPFM really is a combination of AFM mode and a KPFM mode. Now let's take a look how many ways we can have. For KPFM itself, there's AM, which is amplitude modulation detection KPFM, and also there's frequency modulation KPFM. On the AFM side, tapping mode used to be the dominating mode in ambient. 2 years ago, Bruker introduced PeakForce tapping mode. So now we just have more ways to do KPFM. For example, we can combine tapping mode with AM KPFM, abbreviated as TPAM, and this is actually the mode that has been there for a long time. And also you can combine tapping mode with frequency modulation KPFM. Now that we have this PeakForce tapping mode, and we can do the similar combination, we can have PeakForce KPFM AM mode, and also we can have PeakForce KPFM frequency modulation mode. So take notice. The PeakForce KPFM FM mode, I will just give a short name we call PeakForce KPFM. When I say that, that means PeakForce. That's a combination of PeakForce tapping mode with KPFM frequency modulation mode. That will be the focus. I will mention other modes just in case I want to compare the merits of each mode. In that case, I will make references to them. The other thing I want to point out is probably you have heard lift mode, and except tapping mode, frequency modulation, KPFM, all the three other modes are based on lift mode. Let's step back to take a look what's the basics for KPFM. Now let's see, we have AFM probe, and then we have a sample there, and when we bring them together, close together, we can model that as a parallel plate capacitor. Now look at the diagram here. So when you bring these two pieces together, and you know for the sample and for the chip, each have its own different Fermi energy levels there. That is to say, they have different work functions. Now, if we connect these two plates together in the middle here, and the electrons will flow from the high Fermi energy level side to the low side. So leave behind it on the plate some positive charge, and on the other plate negative charge. Now, what KPFM is doing is to measure this difference, measure the work function difference. How? By applying a bias voltage across these two plates of the capacitor, so that it'll bring the charge back to neutral state. So on either of the plates, there will be no charge. So at that point, the bias you applied will be equal to the work function difference of the chip and sample. That's also called the contact potential difference. Again, there are two major ways to find this for KPFM. One is amplitude modulation, and one is frequency modulation. So really, let's take a look. So in the traditional way for Kelvin probe method, for the microscopic method, really what you do is you measure the current, and you see at which point the current will drop to zero. Now, when we combine Kelvin probe method with AFM, and we have a new way to detect when on the plate there will be no charge and when there is charge. And we know for AFM that AFM is good about detecting force or force gradient. Now, if you monitor the force, electrical force between the plates, and that's the amplitude modulation method. And if you monitor or detect the force, the associated electrical force gradient, that will be the frequency modulation method. So frequency modulation KPFM is not just another way to do KPFM. It's a better way. It gives you much higher spatial resolution and better accuracy. Let me illustrate this by a probe modeling. So we did this modeling. So again, when the probe, the AFM probe and the sample can be viewed as a parallel plate capacitor. Now we want to see, and we know that the electrical force is a long-range force. Not only the electrical force will come from the, the very end of the chip, the tip apex, and to the sample, and also it comes from the upper part of the chip cone, and also the large cantilever. So in this model, we have some assumptions. First, we assume the probe body, the tip cone, and the cantilever together is an equal potential body. By that I mean, since the probe is conductive, so and you apply voltage to it, and the whole part has the same potential. And the other assumption, actually, I think it's true, that is the charges, the negative charges, positive charges are only present on the surface. And this is true for good conductors. Now, for the tip cone, the conic body, there we can imagine it consists of a stack of different rings. There. Now, what we want to see is for electrical force, how much the tip apex, how much the tip cone contributes to the total electrical force, and also want to see the tip cone and the cantilever, how much it contributes to the total electrical force gradient. So first, let's take a look at how much the lever will contribute. Again, we check that by how much capacitance it contributes to the whole thing. For the cantilever, let's say it's a stack of different rectangles there, and the capacitance is given by this. Remember here, if the force acting on the middle of the lever or on the very end of the lever, it will cause deflections. So we factor that in as well. For the tip cone, and we'll look at different height. Each ring will how much capacitance it will go for each ring, and then we will integrate to a certain height to see how much the contribution is from the tip apex to a certain height to see the contribution to electric force and to electric force gradient. Now here is the result. So in this plot, the x-axis is the percentage of height versus the total height of the tip cone. Let me go back one slide. So again, the small h is the distance from the tip apex to a certain height. So we'll integrate the contribution, either force or force gradient, to that height. And then the big H is the total height of the tip cone. And there is the tip sample separation there. Now we want to see, again here, in the x-axis is that's the percentage of small h over h, and on the y-axis is the contribution of the tip cone to that height, how much it contributes to either force, electrical force, or electrical force gradient. Now let's take a look at the yellow curve. So if you look at the yellow curve, and for the x-axis, that's 100%. That means if you include all the tip cone from the very tip or the tip to the bottom or the cantilever, and it only attributes to 30% of the signal. That means for electrical force, 70% is from the lever. Now, if you look at the purple curve, which is for the electric force gradient, and that's what the frequency modulation KPFM is based on. And for that one, if you want to get half of the signal, 50% of the total electrical force gradient, and you need to go to here, you need to include 0.2% of the tip cone. So it's a very, very small portion of the tip cone will give you 50% of the signal. Now, if you want to want the tip cone to contribute 90%, you need to go to a height that's 3% of the total tip height. So what this tells us? This tells us for AM, the dominating signal is from the cantilever. And the cantilever, we know the weight is usually a few micrometers. Or, for example, here with the STM-PIT tip, which is a typical KPFM probe, and the weight is 30 micrometers, and the cantilever length is 225 micrometers, so it's huge there. That means the resolution for AM KPFM is really on the orders of micrometers. In that sense, it's hardly, you can hardly call that a nanoscale tool. But for the frequency modulation, since only the tip apex or a small portion of the tip cone will contribute, it's really on the nanometer scale. The resolution we estimate is better than 50 nanometers. Now let me illustrate with an example what's the difference between AM KPFM and frequency modulation KPFM. Again, so the sample is a patent sample that has aluminum stripes and also gold stripes, and in between we have silicon. It's on silicon substrate. Now, with PeakForce KPFM AM mode, and you see the potential profile there, and you probably noticed that although, let's say on the right side here, it's on gold, however, you see a slope there. And for the PeakForce KPFM, let's say again the frequency modulation KPFM, and you see on the gold side it levels. So this is what you expect. It should level on gold, it should level on silicon, and it should level on aluminum. And this is not the case for PeakForce KPFM AM mode. Why? Because although, for example, on the edge of the gold, you think the tip is on the gold, and indeed, from the tip apex, it's measuring the work function difference on gold between your gold and tip. However, your lever covers a much larger area. The lever overlaps or covers the silicon part and the gold part. So when you move the tip along, more toward the gold side, you have, it's a weighted average between different materials. So that's why you see the slope. And on the PeakForce KPFM, though, the transition between silicon and gold or aluminum and silicon is much sharper. So you do not have to use a small feature to see the difference in spatial resolution. So the other thing I want to point out is on the AM here, since it's the average, it's a convolution of the different materials there, and the measurement cannot be accurate because it's a combination. It's a weighted average of the areas covered by the tip cone, and the cantilever. So in order to be accurate, the spatial resolution must be high. And this is pretty much true for the PeakForce KPFM. Now let's see what kind of small feature you can resolve. And the sample here is a carbon nanotube sample laid on gold covered silicon. So on the left is a height image, on the right is a potential image, KPFM image. So if you look closely on the top there is a single strand carbon nanotube. The weight is less than 2 nanometers, and also there's a bundle on the bottom there. It's about 30 nanometers wide, so it's a carbon nanotube bundle. Now on the right side, that's a potential map, And if you look closely, you can see corresponding to the single strand carbon nanotube, you can see there is a potential contrast there. And the difference between the carbon nanotube and the substrate is 30 millivolts. So you probably will be, and you can say, wow, we can see 2 nanometer features. So can we really see, the question really is, can we really see that accurately? Now, if you look at on the carbon nanotube bundle, and the difference is 105 millivolts. What it says is, although we can see very, very small features, we can resolve small features, but we cannot resolve 2 nanometer features accurately. So that's a difference between resolve something and resolve the difference and resolve the difference accurately. Now let me switch on a different sample to see how it compares. Again, here I'm going to compare PeakForce KPFM and the PeakForce KPFM AM. The sample is tin lead alloy, and it has domains around 100 nanometers or smaller. So if you just look at the picture, look at the map, you see, hey, so the left is the PeakForce KPFM, the right is the AM. Now, if you just look at the picture, you say, these two look very similar. The resolution is about as same. The real difference is really in numbers. Now, let's do a cross-section on the same line, and you'll see on the frequency modulation part, the PeakForce KPFM, and the difference between these two domains, the tin and lead alloys, the difference is 240 millivolts, and that's in good agreement with the expected value. We know for tin, it's the work function is 4.42. For lead, it's 4.25 EV, so the difference should be around 200 millivolts. That's what we see with PeakForce KPFM. But on the PeakForce KPFM AM side, we read about only less than half of that. Again, both FM and AM resolve the difference, but FM gives you more accurate reading. The reason is the measurement is more local. The contribution is mainly from the tip apex. And for the AM, it's from the tip apex, the couple part of the tip cone, and also the cantilever, so it averages out to give you a small number. This again says the difference between the revolution and how well you can resolve the difference and how well you can resolve the difference accurately. Let me give you a analogy. For example, now if I stand by my brother and I know exactly I'm 10 millimeters taller than him. Now, AM is like someone with bad eyesight, and he eyeballs me and say, hey, I can see you two, you are taller than your brother, right? And it's about 1 millimeter taller. I said, no way, I'll be pretty frustrated about that because I know I'm much taller than that. You cannot see me, I'm pretty short, so 10 millimeter is a big deal to me. Now for FM, it's like someone with a sharp eye say, you two have different height, and you are about 9 millimeters taller than your brother. I'll be much happier. That is the difference between FM and AM. So FM can resolve the difference much more accurately. So now, let me switch to a different sample. That is a blend of polystyrene and low-density polyethylene. So first, let's take a look at this one. Here, I want to show you that the combination of PeakForce KPFM, PeakForce techno mode with KPFM, afford us with the capability PeakForce techno mode has. It has this quantitative nanomechanical property mapping capability. Here on the top, on the left, the top is the topography, and then it also measures modulus, measures the deformation, which tells you the hardness of the sample, and also the adhesion to tell you the chemical interaction between your tip and sample. So it gives you all those quantitative mechanical properties. And in combining with KPFM, it also gives you this potential map. And it tells you, for example, on the polystyrene part, you will have smaller, it has smaller work function than the low-density polyethylene. So that's one advantage of PeakForce KPFM versus techno mode, where techno mode, of course, it gives you a phase contrast, which is it doesn't give you a quantitative number on whether that's from the modulus difference or whether it's from the adhesion difference, those kind of information. So again, let's come back to our aim. Our target is to have quantitative KPFM measurement. Now we talk about spatial resolution. We know you need to have a high spatial resolution so the measurement will be accurate. But the other criteria is how repeatable the data is. It includes two parts. Let's say you use one probe, you engage different times, you want to see whether you can get the same number. And the other thing is, what if I change my probe, change a different tip, different probe, and can I still get the same number? That we want to know. So after analyzing the sources for the that causes the data to scatter, we found out. So if the operating frequency changes, that can affect your KPFM result. And if the tip sample separation changes, varies, during from measurement to measurement, it can give you slightly different data. So that's on the operating parameters. And for that, our solution is we call ScanAssist KPFM. So we have this software to automatically and accurately find the resonance frequency of the cantilever using thermal tune. It's built in the software to keep the operating frequency accurate on the resonance. And to make sure the tip stays always stays the same distance above the sample, and we fix the oscillation amplitude regardless what kind of probe you use. We say if we know the deflection sensitivity, we can automatically drive that oscillation to a certain amplitude. We now fix at 20 nanometer oscillation. Also, we use optimal phase settings. So that's on the software side, on the operating parameters. The other major reason for a measurement repeatability is the tip work function. We know, again, for KPFM, we are measuring the work function difference between your sample and tip. Now, tip is really your reference. If the work function of the tip changes, for example, due to tip wear, now let's say you have a probe that is coated with metal, like for example, it's a silicon tip coated with platinum, right? If the platinum coating is worn away, and then it exposes the silicon. And we know the work function difference between platinum and silicon is about 1 volt. So that change can give you a big error in measurement. And the other part of problem for reproducibility is electrochemical reaction. Now, especially in ambient, and we are applying bias voltage between your tip and sample. And now, and in ambient, there is usually a water layer present on the surface. So when that voltage is applied, there can introduce electrochemical reactions that can change your tip and change your sample. So that will go problem to repeatability. So this problem is taken care of by probe design. For example, for the tip, we use single materials. For example, silicon. And that way, no matter how you wear the tip down, it's still silicon. It's still the same material, so the work function will not change. And another way we limit, well, I cannot go into a detail about that. So it's a proprietary method. We can limit the DC current flow from the tip to the sample to eliminate electrochemical reactions there, or at least to reduce the reaction by much. So now let's take a look how well we are doing on this repeatability. Here's a set of data. Again, the measurement is on the patent gold, aluminum, on silicon. Now we have two numbers we examine. So one is the number, the contact potential on aluminum, and one is on the gold, the gold color. And the other number is the difference between these two. That's we call the relative measurement along one sample. So what we got here is aluminum. We call that the absolute number, although it's it's a difference between your sample and tip, and we found the standard deviation is around 20 millivolts, and on gold it's about the same, slightly smaller. And the difference also, the relative measurement between gold and aluminum is also pretty small, around 10 millivolts. So that's pretty good. So let me give you some perspective. So in the traditional way, and usually the standard deviation is about 100 millivolts, or sometimes can be slightly bigger than that, or sometimes maybe slightly smaller. But on average, we improve the measurement accuracy by a factor, let's say around 4 or 5. So it's quite a significant improvement. Now let me touch a little bit again on repeatability. Actually, which we know that actually I mentioned briefly in ambient you have a water layer. So you could also control the environment a little bit. For example, we have a 10K glove box solution. Basically, we put AFM in a glove box, and that way we can control the water and oxygen content down to 1 ppm. At this point, we don't have enough data points to be conclusive to say that it helps by how much, but we believe for sure it will help with the repeatability further. Actually, for some samples, for some air-sensitive samples, the glove box will is a necessity. For example, for lithium battery samples, for organic solar samples, it pretty much has to be done in a glove box environment. Okay. So now I want to address another issue that's again, related to quantitative KPFM. So to be quantitative, it must be first artifact-free. And that's our ideal, to make the mode free of artifact. But sometimes we notice artifact can be deceivingly beautiful. For example, here we did PeakForce KPFM on a brush polymer. It has nice brushes, and here is a hide image, and also we see nice images on deformation to tell you, the polymer is indeed softer, and the chin, by the way, the chin is about 5 nanometers wide, so the resolution is pretty good, and also we see adhesion differences on the chins versus the substrate. So it's pretty good, and if you look at the potential map, you see the chins. And initially, we were quite happy about this. We were actually excited. It's kind of beautiful. It shows high resolution. But we want, the resolution is high there. Then we wonder then how true this is. We know that. So since frequency modulation KPFM really is based on the how much the frequency will shift if you have an electrical force gradient there between your tip and sample. Now the way we are measuring the frequency difference is we don't measure the frequency directly. We fix the frequency. Basically, we apply we drive the Kelvin piezo to cause the tip to resonate at its resonance frequency, fix the frequency. Then we apply AC bias to induce a modulated electrical force gradient and to cause the frequency to change. But we fix the frequency and we see how much the phase will change, and that's the phase change reflects the frequency change there. Now we are fully aware the phase. If you have a sample that has strong tapping phase there, it may crosstalk into the FM-KPFM data. So we want to avoid that. So now with PeakForce KPFM, now we figured out a way to tell whether it's an artifact. The way is actually fairly straightforward. So here is what we did again on this brush polymer, and we say we lift the tip. The lift height is we start from 22 nanometers, and we see some contrast, and we just change the lift height 1 nanometer by 1 nanometer, and you can see the difference in the potential map. 23 nanometer, you see the chain actually is getting more clear, and at 24 nanometer, you see a very good potential contrast. At 25 nanometer, you still see something. However, when you increase by another 2 nanometer, and the contrast is gone. What this tells us? That's not what we expect. So we would think if the lift height will indeed affect the data, right? If you lift higher, the resolution will get a slightly poor, and we'll imagine the potential map will be fuzzier as the lift height goes higher. But we wouldn't expect the contrast to go away completely. This tells us the potential map here is most likely is artifact. Why? So when you lift the tip above the surface, when the tip is not clear of the surface, the tip will still be contacting the surface, and it will cause a abrupt phase change, and that will show up in the potential map. Now, when the tip is barely, but completely clear of the surface, it will be gone. There's no phase crosstalk there. So again, let me emphasize, although PeakForce KPFM, we try to make that artifact-free, it's still possible that you have artifact. However, we do have a way for you to identify artifact and get rid of artifact. This is not the case for example, tapping mode tapping mode KPFM FM. And there, again, this is the sample is SBS. It's a polymer, and you see you resolve the so in the middle is the phase map, and you see nice phase contrast there. Actually, that's where you want to be careful. And on the right, it's a potential map. It resolves very small features there. Again, a few nanometers change there. But the thing is whether this is artifact. So the convention wisdom for tapping mode is, why not you just use light tap? You just tap the tip tap the surface very lightly, so it doesn't give you, good big phase contrast. Can you get a decent or a faithful potential map? We tried. So here, if you look at the height, it's not a crispy at all because we use a really, really light tap, and the tip is barely, image the surface, check the surface. Even though we still see a potential contrast, and we don't know whether it's artifact. And there's no way actually for tapping mode KPFM FM to tell whether it's artifact. You cannot raise the tip much higher anymore. Now, for the sample, we switch to PeakForce KPFM. Again, we try the lift height method. So in the middle, if we use a lift height of 35 nanometers, we see very good potential map there. It's very crispy. However, if you just lift a 5 nanometer further, everything disappears. That tells us it is an artifact. The potential map for the tapping mode KPFM, that one is an artifact. And for tapping mode alone, remember that one is done a single pass. So basically, you do height imaging with tapping mode and also KPFM on a single line without lifting the tip. In that mode, you have no way to identify whether it's artifact, let alone to eliminate that. And with PeakForce KPFM, you could. So now, so far we mainly focus on the performance of each mode, PeakForce KPFM. And now let me give you some examples. We showed data on metal alloy, on polymers, and also here is a sample for semiconductor. Here is a solar cell sample, multicrystal silicon on the top surface, and we see potential contrast there, and also another one is organic photovoltaic sample, and it's PCBM and MDMO, and you see the height and adhesion, and the depth is we use illumination to see whether the potential will shift under illumination, and we found the potential downshift about 500 millivolts under 300 sun illumination for this sample. By the way, it's done in a glove box. It has to be in a glove box. And there's an illumination setup, which there. That's just released. I want to also mention another promise for KPFM FM. That is, it has some other advantage. So we know, for KPFM, the sensitivity relies on a spring constant. Why? Because the spring constant is a matter of force, and also it's a sensor of force gradient. Now, when the spring constant is smaller, it's more sensitive. The quality factor of the cantilever also matters. It will further amplify the signal. So really, the total sensitivity is proportional to the quality factor and inversely proportional to the spring constant. For tech mode, though, you cannot do much. You cannot use too soft lever, and the Q cannot be too big. Otherwise, the bandwidth will be limited. And the PeakForce tech mode gives us more freedom. We can use much smaller spring constant. We have use spring constant 10 times smaller, and we can also use a higher Q. There's a potential we can increase the sensitivity much better. If you compare in high vacuum, the quality factor is it's about 100 times higher. So with PeakForce tech mode, we can approach that kind of sensitivity. Now let me briefly summarize what we have talked so far. We focused on PeakForce KPFM. That's the frequency modulation KPFM. It gives us higher resolution, spatial resolution, and associated with that is higher accuracy for the KPFM data. And also we achieved high repeatability through tight parameter control. That's how in the software and also through our probe design. And it also leverage the PeakForce Tech and Q&M capability to give simultaneous mechanical data. So now we believe we have come to a point that we can begin to call KPFM quantitative, and of course it's a high resolution there. Let me switch. I know we are approaching to I'll run a few more minutes, couple of minutes to switch gear to different mode. So we also have a PeakForce KPFM high voltage mode that is to measure high voltage. So you say, why bother? If you look at the work function table, and there's no material that's have a work function above 10, right? So KPFM covers well. However, we recognize there's a need to measure high voltage that's from static charge. For example, if you work on the carpet, dry day, and you get a static charge, and someone told me it could be as high as hundreds of volts or even higher. So, and that's one way is if you to build a high voltage source and do the similar way as KPFM, and you can do it. It's wearable, but we are not keen to apply high voltage to your tip. So what we do is we call that to measure the high voltage the soft way. Basically, again, it comes back to this parallel capacity model, and if you apply voltage, it's voltage there, and it will have this omega term. Let's say you apply at omega frequency bias at a frequency omega, and you look at that term, and also look at the 2 omega term. You can calculate the electrical potential using this formula. Now let me just give you one example. Here is a PDMS sample there, and with this method, we can measure up to 200 volts that we calibrated. The accuracy can be within 15% relative error. And in this example, we measured minus 99 volts, nearly 100, minus 100 volts there on the negative side, and we measured 160 volts on the positive side. So it really extends the potential range much, much beyond the conventional KPFM, which is 10 volts. So since we are running out of time, I'll touch back, give this grand summary. I have shown you the PeakForce KPFM that is quantitative, and it gives high resolution, spatial resolution, and more accurate and quite repeatable. And also it gives you simultaneous mechanical and electrical information. And we touched briefly the KPFM high voltage mode that measures an extensive potential range beyond 200 volts. Now, with this, I thank you for your attention, and we'll open up for questions. I'll hand over to Thomas, to read the questions, and then I will answer some of those questions.
Okay, thank you very much, Chanzeng, and let's try to answer a few of your questions. I'll just go through the list, and again, we'll follow up with email. I see we really have a lot of questions, and I'm really glad about the level of interactions. Let's see. Let me just start sort of bottom up here. Vacuum conditions versus glove box. I mean, in vacuum you get a higher Q. Do you have that too? Do you get vacuum in the glove box, or what other advantages do you have in the glove box?
So in the glove box, we don't run in vacuum. Glove box really is, the pressure is around the ambient pressure. There we don't leverage Q there. No vacuum there.
So another question here about that artifact. Can you explain the artifact? So in that artifact example, we slowly raised the distance in the KPFM measurement, and we saw very sudden disappearance of the KPFM signal. And I see that the person asking indicates maybe a follow-up by email is okay. I think it'll be a longer explanation if we...
Yeah, so I can touch that. I can answer you briefly. So yes, the real signature for a artifact really is there's a sudden change of the potential contrast when you change the lift height. Although, in the software you do not have to do that. Really, you can just look at the tapping amplitude on the lift line to see whether it's close to the free air amplitude. If it's close to that, it's you are guaranteed there won't be any artifact because the tip is not on, not touching the surface. And if you see the amplitude smaller, let's say by more than 10% of the free air amplitude, you need to lift, let's say, another 5 nanometers. Yeah.
Okay, so thanks, Chanzeng. Yeah, another question. The high voltage mode, isn't that one using amplitude modulation KPFM detection? Yes?
Yes, that's in essence the resolution you get is about it's similar as AM KPFM. That's correct.
Another question. Absolute contact potential value change versus lift height. Once you lose the contact with the surface, should it be independent of lift height?
So actually, well, that's a very good question. In some papers, they are talking about the lift height. Although, by operating on the resonance and by using frequency modulation and the potential data dependence on lift height is not that big. For example, for frequency modulation, in some papers they say if the tip sample separation is within 30 nanometers, then lift height doesn't really change the value. However, if it's way above 30 nanometers, then it will change with lift height. So I would say you want to keep that the tip sample separation below 30 nanometers. That's not the same as the lift height because that's not the real separation.
One person is asking if you could briefly explain the difference between PeakForce mode and regular tapping mode. Maybe a longer explanation there.
I can really, in terms of the KPFM performance, I would say, if you do tapping mode frequency modulation, and if you do KPFM frequency modulation, you get similar data. On the KPFM side, they are similar, except in some cases for tapping mode, the artifact is hard to avoid. And the major difference is for PeakForce tapping mode, you get simultaneous mechanical property mapping, and so use.
And there's a lot more to PeakForce tapping mode. We have webinars and presentations on that to just PeakForce tapping by itself.
Yeah, that's a good point.
PeakForce KPFM, is it using lift mode? Yes.
Yes. That's yeah. For all the PeakForce-based KPFM mode, we use lift mode.
In PeakForce KPFM or in general for FM-KPFM detection, frequency shift is measured basically through a phase measurement. The person asks, is that phase measurement of the fundamental resonance or some other high resonance mode?
So it's for the frequency modulation, we are using the fundamental resonance. and that turned out to be more sensitive, more accurate.
The next question, that improvement in the repeatability, is that sample dependent?
No, actually, for the repeatability data you saw in the presentation, we did it in ambient condition, and of course, if your sample is, let's say highly hydrophilic, or then it has some dependency on the sample, of course, or some sample it can be easily oxidized. Then in that case, it's a sample dependent.
So we're really talking about the instrumental contribution, right?
Right. So really, we try to work on the instrumentation side to make it more repeatable.
And I recall quite a bit earlier there was a question: do you furnish a reference sample with the KPFM package?
So for that one, I would say yes. With the KPFM package, we have a sample to go with it. You can use as a standard. Basically, it has the aluminum there and gold there, and also silicon. And the gold is more stable in ambient, so that can be served as a calibration standard. That said, actually, for the probe itself, we made it, the work function to be quite consistent from probe to probe. So if you calibrate one, and then the whole batch will be quite consistent, within an error standard deviation, up to 50 millivolts or better.
And I think you answered also. There was another question on the probe. So yes, the probe is part of the package, and it contributes also to the consistency.
Yes, exactly. The probe is actually one big part for the consistency.
I recall, again related, somebody asked earlier, the person has a dimension icon with fast send capability. Is this available for them, KPFM, this package that you discussed?
Why not, Thomas, you answer this question?
Sure, yeah. So the short answer is yes. It's an optional item for a dimension icon, whether you have the fast scan or not. And so it is available for purchase as an optional item for a dimension icon and, in fact, for the multimode 8. So those are the two instruments for which this is available. Let's see. There are a number of questions about using this for corrosion earlier on, and here's also a question that says, well, when you're in aluminum, don't you have aluminum oxide on the surface, but you're still getting the aluminum work function?
So that's a very good question. For aluminum, it has oxide, and it will definitely alter the work function to some degree. Yeah, that is true, and that is true to all those samples that have oxide on it. It modifies, but if you just look at a series of metals with oxide, and they still follow the trend what their work function suggests.
In your example of sort of AM versus FM mode on the lead tin alloy with microphases, person is asking here, it seemed the topography was disturbing the AM but not the FM detection. Why would that be the case, or what was going on?
Yeah, we did see a little artifact on the AM mode, and honestly, I'm not quite sure why that happens.
Let's see. Another question here on PeakForce mode. Does it lead to faster tip wear, or what is the situation with tip wear, tapping versus PeakForce?
Actually, we have quite some intensive study on the tip wear for PeakForce tapping mode. Since it allows you to use much smaller spin constant, and then the tip wear can be actually much smaller, and also you can use very small force there. So the tip wear actually is much better than tapping mode with a stiffer lever.
Any comment on measuring work function on semiconductors, especially if you have very few carriers? And the question of whether you don't really get a Fermi level equalization then on semiconductors or in those cases?
I can only comment that on what the samples we have used, and typically it's doped. But we also imaged a SRAM sample. It has low doping all the way to high doping. It has P-type, N-type. In the doping level, well, of course, will change the work function versus its intrinsic work function. But we haven't seen any problem detecting the potential or the work function difference across the range we have seen. It's really from 10 to 14 all the way to 10 to 20. We can see the difference.
On the polystyrene beads on that image, it was observed there is a potential variation, I think, within the bead area. Do you think that's real, or is there a question of topography, convolution in the KPFM signal there?
I'm not exactly sure which part you're talking about, but I believe in the polystyrene part there may be some LPD there or some contaminants there. I think it's true. It's real there. But I believe it's real.
On the carbon nanotube KPFM data, would there be a variation of height when the carbon nanotube increases in diameter? Would that affect the KPFM data?
So for to have high resolution, really you want the tip to stay close. Actually, in the probe modeling, I mentioned that of course there's a dramatic difference between friction modulation and amplitude modulation KPFM, and also there's a dependence on the lift height. So you want to stay close for those small features.
Okay. Let me see. A few more questions came in. Will this presentation be available for download? Yes. I mentioned in my introductory comments it will be available for download on our webpage, and as an attendee of the webinar, you'll also receive actually the link where to download it. So yes, on that.
Also the recording.
Oh, the recording, yes. But so you'll have the presentation material that way. A question coming in here. What is the amount of that the cantilever can contribute to the signal? I know you did have a slide on that where you did some careful modeling.
So yeah, we actually the modeling there are papers giving different models there and from different but surprisingly pretty much we got we arrived at the similar conclusion. For AM mode, the lever contribution can account more than half. For friction modulation, it accounts much less. We are talking about really a few %. So it's quite negligible.
A question about the work function. If the work function of the tip is known, so then can you measure the work function of the sample? Do we know the work function of the tip?
Yes. So again, you can calibrate the tip. Actually, we know where the work function of the tip is for the probe we provide. So actually, in the software, we have a parameter. You can type in the work function of the tip, and then it will automatically calculate the work function of the sample. It's there. It's built in.
Another question here: if I put a semiconductor layer on one electrode, and I'm measuring the surface potential, what does the surface potential mean then? Is it the work function difference between the two electrodes?
So I think that's a very interesting question. Really, let's say you just put a very thin layer of semiconductor or metal on some other substrate. What's the contribution from the underlying layer and the top layer? And so for semiconductor, I'm not entirely sure. How much it'll contribute. But for metal, we know if the thickness of the metal is less than 10 nanometer, and then the underlying layer will also contribute to the measurement. For semiconductor, I'm thinking since the charge carrier there is less, probably you need a thick layer, semiconductor layer, to only read the top layer work function. Otherwise, you may see some contribution. I don't know how much from the underlying layer.
Okay, well, thank you very much, Changzheng, and thank you everybody for attending. We're actually significantly over our initially planned time, so we'll have to finish here. Again, we will make this presentation available via download, as we're doing generally with our webinar series. We will follow up with email for further questions. We'll invite you to ask us more questions. You can also find us on the Nanoscale World Forum for more questions on this. Thank you again, everybody, for attending.